So let me. So the motivation comes from the following. So if you look into representations of GLN, so let's say let's consider the group GLR. So representations, irreducible polynomial representations are parameterized by Young diagrams. Of with rows or with at most R rows. Okay. So let me denote YSR to be a set of Young diagrams. With at most R rows and S columns.
And at most S columns?
Huh?
At most S columns?
Yeah, at most, yeah. At most R rows and at most S columns. So there is a duality. So there is a bijection between this. There is not one, but two at least. So you can just take lambda and take the transpose of the Young diagram. Okay, so you can take the Young diagram, exchange the rows with the columns, and then you get this. Okay, so now let's take lambda 1 up to lambda n, n tuple of Young diagrams. So and n tuple of n tuple in YRS such that number of boxes in the Young diagram, and you sum it up, I equal to 1 to n is equal to R times S. Okay, so this is the condition. So if I take the transpose also satisfies the same condition. And now now it turns out that if I take V lambda 1, the modules of S.
I don't understand the word n tuple.
So this is like n Young diagram, right? So
it's n different Young diagrams?
Yeah, n different Young diagrams. Yeah. So that's why n tuple in Y as n tuple. Yeah. Maybe I should just write it this in YRS to the. I mean that's it.
And what is the mod of?
Oh, it's a number of boxes. This means number of boxes.
So it's a bunch of any Young diagrams such that the total number of
boxes is
all
RS.
of the Young diagrams put together is
RS, yeah. So it's a number of boxes of lambda. Yeah. So now with this condition, if I take dimension of the space of invariants of SLR is equal to the dimension of take the corresponding things in this.
So the superscript is in projection on the singlets?
What? Which superscript? No, this is the dimension of the invariants.
Okay.
Yeah, so this is a representation of SLR, and then you take the invariants, and then so this is the numerical equality, and so this is the first motivating thing.
Sorry.
Yeah.
You had all these representations. You have taken a direct product, and then you are looking at in the direct product. You are looking at the singlet under SLR.
Invariants under SLR, yeah.
What does it mean? Singlet.
I think so.
Yeah, singlet. Yeah.
What is invariance? Is it singlet?
No, but it's like so. Yeah, so so these are representations. The group this acts here, and then you look at the space that doesn't move, the subspace of vectors in here that's invariant under this action.
So this is okay. This is singlet. Okay.
Okay. Yeah.
Why are you interested in SLR?
Oh, because GLI will not get much because there's always the determinant representations that mess up things. Okay. So now, so where is this? So where is this coming from? So and then what is this number inequality? Let me just explain. So okay. So let's look at the Grassmannian of R-dimensional subspaces in R plus S-dimensional space. So there is a duality, there is an isomorphism between this, just by taking the quotients. So this number, so if there's an isomorphism, of course there's the cohomology spaces are same. And so these numbers have an interpretation in terms of the structure constants in the cohomology spaces. So these things have a basis. So
Sorry, it's going too fast.
Yeah.
Grassmannians is what?
oh, Grassmannians are R-dimensional subspaces in R plus S-dimensional space, right? So there's a duality, right? Because
So there's an R. So what does that GR symbol mean?
the Grassmannian.
Okay, and what? So can you define what a Grassmannian?
Yeah, sure. So Grassmannian. Yeah. So Grassmannian. So fix a vector space W. So this is just, as I said, is a collection of.
A set of subspaces.
Yeah.
I see. Thank you.
So this is that dimension of V is equal to R.
The set of R-dimensional
So
subspaces.
spaces of a fixed R plus S dimensional space.
Okay.
And then you just take the dual, right? So there's a duality, right? Because the quotient is of same dimension.
Yes.
Or you can just take the corresponding dual and then dualize the exact sequence. So if there's isomorphism between the Grassmannians, then there's isomorphism between the cohomology groups, so the topological, all the constants. So these things are actually structure constants in the cohomology. Okay, so how does this thing show up here? So this is a completely representation theoretic object. How does this show up in this topological objects?
So and for this to be true, you need an inner product. Does the space have an inner product or is not?
Which space?
The vector space of whose Grassmannians you're computing.
No. This is just because you have a V, right? To W mod V, right? So this is R dimensional. This is R plus S dimensional, but you can just take. Yeah. So, but if I am just identifying the state to be C, like this state standard one, like C. Yeah.
The way I understand this isomorphism is by if you have space of R planes.
Yeah.
Transverse to that would be the space.
The space of S plus.
But transversality means.
Orthogonality, but yeah, I mean here I'm just taking. You can take this W to be C R plus S, so you can take that. Yeah, so you can take that. Yeah.
So then it has it.
Yeah, that's an linear product. Yeah. Okay. So right.
What kind of cohomology are you considering?
Just cohomology with Q coefficients. Yeah. So these things. Yeah, Q you can take Z whatever you want. Yeah. You can take Z also. Yeah. It's fine. So the singular cohomology, not anything fancy. Yeah. Yeah, so then, so these things have a interpretation in terms of structure constants here. So these things have a basis. So there's a.
I'm really sorry, but I don't
Yeah.
understand what 8 star of GR.
Oh, so H star is the cohomology group.
You're going to have to explain it. Cohomology.
Okay.
I mean, if I got a differential operator or something, I understand cohomology.
Yeah. So well, it's a smooth manifold with differential operators like the closed form modular exact forms, right?
There's a D operation.
Yeah, I mean that's the complexified ones, but then you can take the.
Okay.
But that vector space comes from taking the Z vector space and complexifying that vector space. Anyway, so okay, so okay. So what I want to say is that these guys have a basis, some geometric basis, some varieties.
Can we think in terms of homology?
Huh?
Can we think in terms of homology?
Yeah. So yeah, of course. Yeah, this is a dual basis.
So when
Right?
you say geometric, that's what you mean.
Yeah, that's what I mean to geometric. So I mean,
So can you state this condition in terms of different? Is there a way of stating this in terms of DRAM cohomology?
which condition?
The first of all this isomorphism and why this is a statement of cohomology.
Which one? This one?
Yeah,
If two spaces are isomorphic, then
say if I consider the spaces as let's say R a real number, so R to the n,
Yeah.
n is R plus S.
yeah,
So these are like R planes. First one is a set of R planes,
yeah.
and the second ones are like the
Set of S planes,
Given
yeah,
an R plane, you look at the orthogonal subspace.
yeah.
So since like you can state this condition in terms of differential forms, is there a way of why is it related to cohomology?
What do you mean? Why is it related to manifolds are isomorphic? Then their cohomologies are isomorphic. I mean,
If two manifolds are isomorphic,
then the cohomologies are isomorphic, right?
which cohomology?
Any cohomologies like singular cohomology, DRAM cohomology, whatever cohomology you can come up with.
First of all, wait, why is it a topology? you
No,
have
it's not a
some
vector space.
subspace.
It's
Not a vector
Where
space.
is the topology?
Not a vector
Have you
space.
defined topology on it?
okay. If I
What
start
is
doing that, then I
topology?
will take like a semester to complete my talk. I mean,
No, but it's clear, right? Rachmanian, so you should be familiar. So these are just a space of R planes inside an R plus S dimensional space. So this is one point on it, this is another point on it, this is the other point. And continuity just means this.
And
This is the root topology.
should I think about this R plus S dimensional space as something R to the real R to the power R plus S?
Always a finite dimensional vector space isomorphic to R to the power R plus S.
yeah.
Vector spaces. Yes.
Yeah.
And then you are giving the topology by the induced topology from R to the power R plus S.
No, it's a
It's
quotient
metric
topology.
It's the standard.
Yeah, I mean,
metric
then
topology.
you have to quotient it by the transformations that are keeping the R plane fixed.
It's the standard topology of real numbers. That is the topology you are using.
No.
This point is close to this point. This point is close to this point.
Close means you need to define a metric, which is the standard metric in R.
Close meaning topology.
No, so what you can do is, okay, one way to think of this is that, okay, so you can take the R dimensional space, take the top wedge power, so you land up in some big projective space, and then that has a topology, then put the induced topology under the closed embedding.
Okay, you are
Embedding.
taking the induced topology from, let's say you are in R3, then you can define a standard topology in R3. So I'll assume that you are taking that topology.
That topology will not give you a topology on this. Let me just say that.
Maybe one example could be that.
Can you give me one example? What is the topology?
So P so like take the very
Give me
best.
R
R equal to 1, and this
and
is
S equal to 2.
this is the projective space, right?
Yeah.
So what is it? So 1, 3 is what?
With the projective space, or like lines in three-dimensional space, right? So this is RP2, right?
And then the topology on RP2 will
Well, you can just take take the one complement and then quotient by C star, right? That's the quotient topology.
And then
You have the cross step.
And the topology that you are getting is the induced topology from the. So before you.
Not the induced, the quotient rather.
What do you mean by not induced?
It's called quotient, not induced. Induced is something for a subspace, not for a quotient.
Maybe that's what he has in mind.
Okay, so that, or then it will be very hard for me to explain. Okay, so anyway, so these things have a basis with. So anyway, let me just going to give the. So this space GR of R plus S has a basis with respect to some stand. So this is as a vector space. This has some basis with some varieties. I'm not going to define these varieties, which are parameterized by YRS, and the intersections.
So I should think in terms of homology now.
Yeah, you can think of it as a homology. Yeah, this is a homology basis because it's smooth variety, right? There's always Poincare duality and all kinds of things go on. Yeah. So these are varieties, and then you can take n of them and then intersect, right? So let's just pretend that these varieties are smooth, though they are not, but intersection still makes sense.
So this is a bit fast that these varieties are labeled by YRS.
Yeah, this is a theorem. This is a non-standard theorem. Okay, and so this is a basis as a vector space, and there is also the multiplication, right? But then you can, because of the cup product, so then you can intersect the varieties, right? So if you take
What is the dimension of each of these varieties
yeah.
in terms of RS?
No, you can compute it. So the code. So I can tell you the codimension. So the codimension of this is the number of boxes in the Young diagram. So this condition is guaranteeing that the intersection is only a finite number of points, right? Because that's this condition guarantee. So it will be a number of points. So these points is actually the number. Is actually the dimension. The dimension that I'm counting. And so then one can ask, well, there is isomorphism. Where does these classes go under this isomorphism? Okay. So then, the thing is that. Yeah. So this condition guarantees that this is this intersection is a number of points, right? And then the number of points in the intersection is equal to the dimension. So that's the count. Okay. So this is why this condition is coming up. And
it's the fact that it's the fact that it is the intersection is just a bunch of points.
Yeah.
It will happen
The codimension sum to the dimension, yeah.
And
There's a
that
transversality
is
condition.
Because the dimension of with Riemannian is RS.
RS, yeah, because it's always n. So yeah, so it's this thing and then the times the difference of this with this. So and then under this isomorphism, I can ask what happens to the Schubert basis, and it's no. So there's isomorphism right out here, right? Yeah. So there's a subvariety here. You can check where the subvariety goes, and this subvariety goes to the one with corresponding transpose, and this is equal to the dimension.
But is there any way to see how is this classification? Why is the variety? Why is this basis of homology classified by particular camera?
Oh.
Is there a way to see?
No, this is not such a nice proof. There's some algebra, and then some algebra is generated by classes of this. Not it's only in. So this is yeah, that part is not very.
In terms of maybe some rectangular matrix divided by some square matrix, and then.
No.
No.
Yeah, I think this is the cohomology. That's now the Bruhat decomposition stuff. What?
The last line is you mean lambda 1 transpose.
Yeah, right. Yeah, so these classes have a description in terms of whatever, like in terms of matrices, but the fact that, I mean, these classes can be defined, well, like I cannot do it right now, but this case can be defined in terms of the Bruhat decomposition, but the fact that that they span the cohomology is coming from basically the fact that this Bruhat, this is basically gives you a cell decomposition. That there's something called a Bruhat decomposition of Grassmannians, and the Bruhat decomposition is a cell decomposition. So once you know you have a cell decomposition, then you can compute the cohomology in terms of the cell decomposition. That's more or less the proof.
Is there a way of defining this cohomology in terms of differential form? I am not understanding the cohomology. Can you define it in terms of DRAM cohomology?
Yeah. Okay. So well. So X is a manifold. Well then, H star of XZ tensor C or tensor R is basically say HI command is just basically closed I forms modulo exact I minus 1 forms.
Great. So now this GR R comma R plus S, this is considered as the standard with the standard open set. This is a manifold, and in that you are just classifying the. So what is H star? You have defined HI. What is star?
H star is the whole direct sum because there is a ring structure also.
H star is the direct
Sum
of
over
HIs.
HI, yeah.
So H star is supposed to be the direct sum of all this
Yeah.
differential forms.
Yeah.
What about the manifold? Is it like simply connected? I don't know the structure of this manifold. This GR.
Manifold is connected, yeah.
Is it simply connected?
It's a quotient of it's a yeah.
As a manifold, is
Yeah.
connected, you said?
Yeah, it is simply connected. Yeah, it's simply connected. Yeah.
Because that depends on if you can use the pocket lemma or not, things like that.
No, it is simply connected because there are only cells in event dimension. Yeah.
So it's a simply connected manifold.
Yeah.
And this is a sum over all the all these forms.
Yeah.
Which is the sum of these quotients.
Yeah.
And then what was this statement? What is this C? Can you define this sum? What is this?
No, so this is a ring, right? So this is a vector. It's also a vector space, right?
It's also a vector space. Okay.
Yeah. So the vector space. I'm just writing some basis of this vector space.
Some basis of the vector space.
Yeah.
And what are these bases? Can you
So these bases are some. So these are some sub varieties in here. Okay.
What is? I don't understand variety. So is it like some subclass of differential forms?
You can think of that. Yeah. So top degree forms. Yeah.
So you have only top forms?
No, because this is this is what's called a fundamental class, right? I mean, because this is not a smooth variety. I don't know. I want to go. Just think of this as a basis of. So just think of that. Is
this line an equivalent sign or is that an isomorphism? That sign that you have.
Well,
this is an isomorphism.
this is a basis, but there could exist other bases. Yeah. So it's a.
So is it
isom.
the basis of differential forms?
No, it's not a basis of differential forms.
So it's a basis of some other thing which is isomorphic to the structure of differential forms?
I don't know what the differential forms are coming in here.
Because you just said this H star is direction of spaces, every
So I don't-
space is closed by exact.
No, but this is a subvariety, right? So think of them as a submanifold, right? In here, and then you have a top dimensional. So submanifold has some top dimensional form, right? So they take the image of that thing. So
In 8 star, I have a sum over different classes. Every class is a class. Let's say ith class will have this ith closed form by ith exact form. And can you define this?
so do you know? Okay, so there is a So if you have a submanifold, you have submanifold. So think of a submanifold inside a manifold, okay, right? So then you have a map between the homologies. Do you understand homology?
I understand homology.
Yeah. So this is think of this in homology because there is a Poincare duality in here, right? So there is a map. Yeah. So there is a map from here to here, right? Okay.
Yes.
So if this is a subvariety, this makes sense up here, right? Correct.
What is Z here again?
So some
In this example, what
Z is this guy. X is the Grassmannian.
X is a Grassmannian and Z is some subset of the Grassmannian.
Some
Submanifold.
some submanifold you can say. Okay.
It's some cycles.
Yeah.
Model boundaries.
And then
Just homology.
you can take the homology, right? Goes to the homology of this, and then you can just apply Poincare duality to go to the cohomology. So that's what is happening here.
Okay, so each omega lambda is a submanifold of the Grassmannian.
Yes.
And you have written and what is C of omega lambda?
The span.
And such a decomposition exists. This is a theorem, which is some big theorem. Okay.
Not very deep, but the fact that it's a Bruha decomposition. That's all.
Okay. No. But how the even span with omega lambda and every lambda belongs to.
Yeah, it's not that.
That doesn't sound like very.
No, it's just because of the fact that if you have a general linear group, right? You can write a decomposition like this in some wild group, and then you are taking out some parabolic. So there's some p. So there will be some things in here, p. So maybe you should put a b here, and then you have to take some wild group subset. So and these varieties are like closures of these varieties.
I would suggest, I think this was just the motivation.
Yeah, this was just the motivation. Yeah. So yeah.
This is the motivation.
Yeah. So this is the equality that one gets, and actually one can show that this is actually a duality between these vector spaces. Okay. So now one can ask. So these vector spaces are dual. So there is a perfect pairing on these vector spaces. There's a pairing which is a perfect. Okay. So now one can ask what happens. Try to generalize this for other groups or other pairs of groups. Okay. So that's where it comes from. So that's where. So I think there was a paper of Nakanishi and Tsuchiya around '94 where they do suggest that this type of things can be generalized using conformal blocks. Okay. Of the WCW model. So let me. Okay. So any other questions, or I can. Yeah. Any other questions? Are you happy or? Okay.
This Grassmannian, okay, maybe that's what you will say, but I will just go because how did you relate the Grassmannian to the initial group that you started off with?
Oh, because yeah, right. That's a good question. Because the Grassmannian, right, of R planes in this, right. So you can write it as a
In terms of matrix.
yeah, it has a matrix, right, as a quotient of these things. Yeah. All right. Yeah. Okay. So okay. So there is one more level. I guess.
Sorry, just to understand this previous comment of yours, you can think of this as R-dimensional square matrix is sitting inside R plus S dimensional.
Yeah, with some particular rank condition.
With some particular
Rank condition. Okay. Yeah. Okay. So let me. So I mean. Okay. So. All right. So let me go and let me give you a very a definition of conformal blocks.
So
That
when we say level 1 duality, it is a statement about the duality of those vector spaces. That
yes, there's a duality of those conformal blocks. So what happens? Okay, let me instead of saying what happens, let me just tell you what exactly happens. Okay, so let's try. So just remember. So the objects of interest for us are invariants of representations. So yeah. Okay, so let's try to refine these spaces. Okay, let's try to put some, bring in an operator and refine the spaces such that asymptotically it becomes this space. Okay, so this was done. So this definition of conformal blocks, this particular definition is due to Shekman, Varchenko, and Boris Fagan. Fagan. So what they do? So now I'm going to go in the general Lie algebra setup. Okay, so G be a simple complex Lie algebra, Lie algebra, and then I'm going to take so as we all know, so that this set be the set of dominant weights, dominant integral weights. That means all representation theory is of G is parameterized by this discrete set, and I'm going to cut off this discrete set by an integer, so lambda in P plus of G, such that lambda theta is less than equal to L. Okay, so you can theta, where theta is the highest root. Okay, so for SLR you can take theta to be this matrix. Right. So all zeros and 1 at the very end, and so let me just give you an. I guess can I write here? No, maybe. So example. So if you take G equal to SL2, right? So we all know that irreducible representations are given by symmetric powers of this, right? So this I is the. So basically, you just need to know. So this set Pi of G SL2 is just Z plus. Okay, so these are what are called, I guess, in physics literature, it's called as spin half representations, right? And then so P L is just integers all the way up to 0, 1, 2 up to L. Yeah. So you are cutting down the cone. So this is in general a cone, right? And then you are cutting the cone by some hyperplanes. Okay, so now these are all constant vector spaces, which is kind of boring, but let me move them around so I fix Z1.
PL is not a set of representations?
Yes, PL is a subset of the set of representations, right? So it's a finite set.
Integrable representation.
Yeah, it's called it's what's called integrable representations of level L.
P plus equals Z plus, and you called it spin half representation.
Yeah.
It's not quite. You want to think of it as a set of representations.
Yeah, the set of representations, all of them, yeah. Right. So this I integer is the correspondence, and then you're just cutting it out of it. Yeah. So right.
And roughly, I should think about L being the level, roughly at the end.
Not roughly, exactly the L. That's the level. Yeah.
That depends on your normalization.
Yeah. So normalization in Lie theory is always such that the length of the highest root is 2.
K is also, cares about the normalization.
Yeah, but so in
Normalization is exactly.
no, the standard normalization is the one, right? So theta is equal to 2. This is the standard normalization. Okay. Yeah. Okay. So this is Z1 up to Zn are points in complex numbers, C to the n, so that Zi not equal to Zj. Okay. So you can think of n points on a curve, and then I'm going to introduce an operator. So let me call this Z. Right. So this is Zi, and I'm going to so Zi. So let me define the action of this operator. Operator on V1 up to Vn. So Vi's are in some lambda i's. So this is by definition the action is given by you scale and then x theta. So x theta is this one. gi, and then you don't do.
You are picking the vector in some direct product representation.
Yeah, and then I'm just giving.
And you are
I'm just acting. Yeah. So this is the formula by which it acts.
okay.
I equal to 1 to n.
Just a set of n numbers.
Yes. Yes. Yeah. So this is not like a representation, the diagonal action, because there is all these zi's here, right? So if all these zi's are equal, then this is the diagonal action.
This is the diagonal action.
But then the zi's are never equal.
There's a notation here. X theta.
X theta. X theta is just the root space corresponding to this theta. So x theta is just this matrix. Okay. So then, so the space of conformal blocks. So I have G, I have L, I have this.
So it's breaking the symmetry between theta and minus theta. Sorry, it's x theta is what again?
X theta is just this space in the Lie algebra whose root is theta.
Theta was
Theta is the weight for that space. So theta is an element in the curtain for which the dual curtain for which in which the torus acts by theta. So theta is a linear form, right? It's in the root space.
Right.
And
you are distinguishing between theta and minus theta. This is only theta.
Of course, I am distinguishing between theta and minus theta.
So here the definition of x theta and x of minus theta are different.
Of
right?
course, yeah. So this will be the upper triangular and the lower triangular, yeah.
Right. So you are choosing one of them.
Yeah.
Mhm.
Yeah, but it's like standard in representation theory because you choose a Borel.
Highest of the lowest.
Yeah. Okay, so this thing is just going to be the following. So I'm going to take V lambda 1 tensor V lambda n. Okay, and then I'm going to quotient out by the G action. Okay, but then I'm also quotienting out by the image of Tz to the power L plus 1
The first question is out
by G action.
G is what?
G is the Lie algebra, right? That's acting. So these are modules for the Lie algebra. So I'm quotienting out with G action, but I'm quotienting out further. I'm quotienting out by the image of this operator.
The Lie algebra acts just in finite dimensional matrix.
Yeah, everything is finite dimensional here so far.
It doesn't act on the z's.
Yeah, it doesn't act on the z's. Yeah.
This was tz to the power.
L plus 1, the level L, because this is the definition of the conformal block. Yeah.
What does that line mean? Image of tz.
No, because
tz was an operator on the.
yeah. So you are quotienting out by anything. So this is the space, okay, on which t to the power. This is the largest space on which the t to the power z L plus 1 acts trivially, and also g acts trivially. That's what I mean.
So you have defined tz. You can define product of two tz's. So
Yes,
you have
just
taken L
compose.
plus one products and
Composing. Yeah.
Taken that image.
I'm just quotienting out all things that are in the image of that. Okay, so
So this is going to give you a conform block on a sphere with n
mark
punctures.
points. Yeah, exactly. So this is
With
so
z as the
Z as the mark points. Yeah. So now observe. Let me just I can try to connect. So L, if L is big enough, right? So then all these actions Z x thetas are nilpotent.
And then the notation of division by something plus something is
It just take the span.
the
Span. Yeah.
both of them.
Yeah. Yeah. So x theta, the action is nilpotent, right? So if you take high enough power, there's 0, right? So for L high 0, there is nothing coming from this contribution, right? So you got back just the space of co-invariance, and so you recover the earlier space that I was working on. So if L is so let me make a remark.
Large.
Yeah. So if L is large, t to the z to the power L plus 1 is 0.
It is large compared to n.
No, this could be. It could be. It doesn't really. It doesn't really depend upon n. Yeah, n has nothing to do. It's a representation theoretic object.
So tz cared about n, right?
If you want it to be greater than n, right? Because the size of the matrix.
No, but the size of the matrix is not n. N is the number of mark points.
But
No, not
definition
n.
of tz cared about n.
R. What was it? Sorry.
Yeah, it's in the Lie rank of the Lie algebra.
Right.
Yeah, yeah.
N is different. R is what you meant.
You might probably meant R.
N times R.
Yeah, so I mean it's not a very. I mean the bounds are not so clear. I mean yeah.
Because it shouldn't hit the edge.
Yeah.
mean, when you couple and you get
Yeah, you could,
and
okay, of
you
course,
exceed,
yeah, it could exit, but sometimes it
Then
could
you
be
can't.
sharp. Yeah, I mean, yeah. Yeah.
But what is this physically? This one is like conformal invariance. This is Lie action of the Lie algebra is like the conformal invariance.
Hmm.
Oh, what are these?
It's somehow he's imposing the constraints.
The constraints of the solution. Yeah.
Constants of
the singlet condition, right? You demand that your correlation functions are annihilated.
which is this G part, right?
Which is
No, but that would just be Lie algebra. But now suppose you impose the constraints, you think of it as a function, and each element belongs to the Lie algebra. And then you impose the Ward identities of the Weissman theory. That's what we think of as conformal blocks, right? I think that's equivalent to this statement.
No, that's correct. Yeah. So yeah, if I were to try to write down the KZ equation and try to solve the KZ equation, this condition comes
I
from.
don't understand how the two are related, but that's what
Yeah.
This is I know that. Yeah, okay. You didn't explain that.
I haven't understood.
Yeah, but this is my definition. But yeah, for conformal blocks. But I will come back to another definition. Yeah, which is more. Yeah. So then, So then one can try to understand what is going on with this. So this is a conformal block, and then you can try to produce statements on rank level duality on these objects. Okay. Right. So that's the.
So in the case where the representations are kind of small, where you don't have to quotient it.
Representations are small.
By this T quotient is kind of trivial.
Yeah.
Right.
Yeah.
If these are not very large representations.
Yeah. So then you get back the space of invariance, right?
Yeah,
That's the whole point. Yeah. So yeah. So that's why I said that you can. I'm refining.
What happens to Z?
No, Z is just not contributing anything, right? So this operator is 0, right? So because it's just seeing.
Yeah, exactly. But don't you expect even in that case to be conformal blocks to depend on Z?
No, you get a trivial vector bundle on the
space
whole
of
thing.
conformal blocks.
You get a trivial vector bundle. It's there, but it doesn't depend upon Z.
The form of the block is a function of Z, of course.
Yeah.
Yes.
But the number of
Number of
conformal
blocks.
blocks
Yeah.
is independent.
Is independent. It's just.
It just reduces it to normal
Yeah.
vectors.
Yeah. But this is the form of the block, this function of Z, right? This is a coordinate dependent.
No, I think he's talking about the space of
The space of blocks. Yeah. The space, right? It's a vector space, right?
Yeah.
Yeah. And the vector space doesn't depend upon the Z's if the level is too high.
It's like the Hilbert space of Chern-Simons.
Yeah. Yeah. Okay. So now let me. Okay. So this is the motivation where. So this is the end of the motivation of how to go to why I want.
Why would the space depend on Z anyway?
Well,
Why would it?
because of this.
I was thinking of this as conformal blocks.
Yeah, this is conformal block. So this depends upon Zi's, right?
Each block depends on Z.
Each block depends upon Z.
How many functions of Z are there?
Yeah.
So that of course doesn't depend on Z. The answer to that question doesn't depend on Z, but it may depend on L.
Yeah, it does depend upon L.
Yeah. When L is large enough, it doesn't depend.
Doesn't depend, right?
Doesn't depend on L.
It does not depend on L.
Yeah. So if you just hit the threshold, right? If it's
This is a function of Z, right?
Yeah, but you're asking how many such functions are there?
yeah, it's a space, right?
Space of such functions.
That is not a function of Z, right? So this is not to be a function of Z.
Yeah. The space of conformal blocks is not a function of Z.
Yeah, right. But it just, I thought it's, why do you put as an argument there?
Which one?
V as a function of.
No, because it's a vector space, right?
He's looking at all those guys and then asking how many of these are invariant
Under
this
and this and that, yeah.
It's a notational condition about V is lambda and then
Yeah, I thought it's a function
looks like
of
an
Z.
argument, right?
Yeah.
Which one?
I think this is a space. It's
For
not
each point,
not a function.
No. So that's okay. Yeah. So maybe so if you think of Z as a point on the
on CN,
on Cn minus the diagonal, for every point I'm describing a vector space, and this is the definition of the vector space.
As you move in that point.
Yeah, as I move in that point, the vector space depends upon Z's. Yeah.
But changes up to only this weird thing. This.
Changes
coming
this.
back to something else.
Coming back to something else. Yeah.
The monodromy.
The monodromy. That's this.
Not some continuous type of thing.
Yeah. So the changes will also depend upon monodromy. That's the connection there, right? But what I'm saying that as a space, underlying vector space may not depend, but the monodromy is good. I mean, you can have non-trivial monodromy on a trivial bundle. Okay, so
Because this connection, what is it?
the Kiznik-Zamolodchikov, yeah. So it's up here, right? So yeah, but you can have non-trivial Kiznik-Zamolodchikov connection on a trivial vector bundle. Yeah. Okay. Right. So this is like so far the end of the motivation. I guess any questions I will yeah, we'll happy to answer any other question. So that's the reason I want to consider conformal blocks. Okay. So now the question is that how to relate. So now so in the very first.
One question. So far you haven't taken into account that the operator is conserved or not. It's so far the operator is not at all conserved. It's just the representation.
I don't know what that means. The operator is conserved. Yeah. There is no.
You have a conformal field theory. You can have operators which are hitting the immutative bound.
I don't know how to interpret it in my language. Sorry.
Kinematics.
That is fine, but so far suppose you are making the connection with the conformal field theory, then this will be related to the blocks in which the external operators as representations given by these lambdas. Lambda 1.
Yeah, the primary fields are highest bit
these are the
vectors.
primary fields.
Yeah.
It could be that one of the primary field is related to a conserved operator.
I don't know what that means, so I will not be able to.
Del mu J mu is 0.
No, I don't know what that means. Yeah, sorry.
You cannot conserve trace.
Oh, we can talk about this later. I mean, yeah. Let me get back.
They're all analytic.
Yeah.
They're all analytic. So in that sense, all good.
Okay. So the question. So now let me go back to the definition of conformal blocks. So this is like just a working definition. Like this is like some definition to motivate the problem. So let me go back to the original definition of conformal blocks as defined by Tsuchiya Yamada. It's also known as the WZW models of conformal blocks. Yeah, no, I'm not. No, so I'm going to define it. So yeah. So again, so I hope this is okay. Let me. So you take the central extension of the loop algebra, which is the affine Kac Moody Lie algebra, and then so this has a Lie bracket f x to g. Plus residue at t equal to 0 g df tensor the Killing normalized form and so on. Yeah. So this is the affine Kac Moody Lie algebra, and then representations. I'm looking at
That line G times C of T.
round brackets. Direct some C, right?
That is the central
So there's a central charge. Yeah. This is a central extension of that.
And this is just the commutation.
This is the commutation relations. Yeah.
X
So
belongs to what? X belongs to your Lie algebra. G F belongs
so the function. Yeah. And then C of G hat is 0. Yeah. Okay.
C is related to the level of the.
Yeah, C is at a level. Yeah, right. So okay, so now, so for every lambda in P in here, one associates a representation which is infinite dimensional. So this is called these are denoted by H lambdas. So H lambdas, these are like Verma module constructions, but these are infinite dimensionals. And so let me just denote some properties. So the highest weight module V lambda sits inside here. So there is a so the operator C acts on H lambda by multiplication by L, and yeah, and then so the Lie algebra acts locally nilpotently. The Lie algebra.
So then when you write V lambda, that's your Lie algebra representation, right?
Yeah. So this is a
H lambda is the full module.
yeah. So this thing is the representation of G hat, and this is a representation of G.
This is the 0 level.
The 0 level guy. Yeah, exactly. So the Lie algebra acts locally nilpotently. Locally. It's a representation module. It's a representation of the primary. Yeah. So it's the same as here, right?
Right, but this was a representation of the Lie group.
Yeah.
Lie algebra.
Yeah. But that's not a Lie algebra. It's a module.
You have centrally extended it, and then you are considering representation of the centrally extended one.
Yeah. No, but then there's this factor.
This is supposed to be the Kac Moody or not?
Yeah, this is the affine Kac Moody Lie algebra.
This is the affine Kac
T
Moody
is giving you the mode numbers.
Yeah.
T is giving me the mode numbers. And just one minute. What about V lambda? Does it contain any null primary or not? Your assumption, and this is not important.
What null primary? I guess that means the highest weight vector. What is your notion of null primary? It's like
You can have a descendant which is null.
okay, well,
Which will be Do you have any descendant which is?
Oh, sorry, I can't really answer your question, but I'm not understanding the question. Yeah.
I'm asking that. If
No, you can ask, but I cannot. You got to ask in my language. Yeah. Sorry. I mean, yeah.
I mean, it's just one of the integrable representations.
Yeah, it's one of the integrable.
It's just the primary for the representation.
Is the primary for the
you have
representation.
the primary and you're building up the representation on top of it. It might be that at some point you are hitting a null state.
Yeah, you might, and that is given by the early algebra representation. In fact, if you include both Virasoro and Kac Moody, there are plenty of null states. That's what
Yeah.
the English sum logical equation is.
Yeah.
Expresses the fact that you get all of these representations.
Right. So you can have null states.
Yes.
And here the quotient that is taken, it takes care of every null state will give me some equation like this, right? So this takes care of all the null states.
Yeah.
This is the full representation.
The full. Yeah.
So it takes care of all the null states.
Yeah. I think.
I think
Yeah. It's a very non-trivial statement, by the way. Yeah.
I could have.
Yeah. This is the statement. It's the Fagan, Shekman, and Vatchenko. Yeah. It's a quite a non-trivial statement. This one. Yeah. I think I don't know if you have geometric proofs. Yeah. Okay. So well, this acts nilpotently, and then So then. Right, so then one can define conformal blocks associated as follows. So if you take so you take C be a curve, be a stable.
So sorry, just going back to this equation, these grading matrices and things like that are the ones that the matrices that act on V lambda as you take Z around something, right?
Yeah.
Non-trivial connection.
This is quite non-trivial. Even just try to work with SL2 with 4 points and C2. You get some non-trivial gamma functions computation there. Okay, so C be a stable curve, which means that it could have singularities, but singularities are node, and then say P1 up to Pn are n distinct marked points. And then I'm assuming that C minus the mark points are affine. So then I'm going to define conformal blocks again. Second definition.
C is a curve in CL, right?
Yeah, C is a curve. C is a curve, stable curve, but it could have higher genus. So mark points of genus G. G. So you can take a Riemann surface, right? And then you can have so stable, just ignore the stable part. Yeah, so the stable basically means, by ignore I mean you could have nodal singularities and then you need to have some stability conditions saying that.
The space on which you're measuring your correlation.
Yeah, the space, maybe you can say that, yeah, okay. And then, but this is a curve of higher genus. You can take, so here only I'm considering genus 0, yeah. But here I'm considering higher genus stuff also. And then I'm assuming this is affine so that I have functions to quotient out. And then the definition is that, so the curve, the Lie algebra, okay, I may have changed the order of things, okay. The curve, the Lie algebra, and C. So I'm just going to define it to be, I'm taking h lambda 1 up to h lambda n, and then I'm quotienting out by G cross functions on the affine curve acting on this thing.
This is not G hat.
No, this is not G hat, because if you take G hat, there's the sub-algebra of this. This is because the G hat is only local, right? It has a local picture, but you want the global picture of the curve to come in. So this is the definition of conformal blocks.
So this reduces to this somehow?
Yes, very non-trivially.
You cannot do this?
The level is here because in the integrable representations. Yeah.
You cannot do this just with V?
Just with what?
V.
Which one? This one? No, I don't understand the question. Sorry.
You were saying this was defined in terms of V. That you
No, that was H. Yeah.
You cannot do this with V.
No, because it's a higher genus. Yeah, it doesn't work. Yeah. Yeah, because higher genus, the co-invariants are not good enough. Yeah, the co-invariants are the finite dimensional ones. Yeah.
And I didn't quite understand the denominator.
So this is so this is a Lie algebra, right? So you have the functions on the punctured curve. Because I assume the curve is affine, so there are a lot of functions. And then you have the Lie algebra, right? Just take the Lie algebra and then the functions, right? So there's a
Tensor product is in the same way.
yeah, there's a tensor product is the same way, but then if it's a global function, right, the sum of the residues is 0. So that's why it's a sub-algebra that maps in here. So that's why these guys act on here, right? And then you're taking the quotient with respect to that action.
So what is the second factor of the quotient?
Which one? Here.
That h is the h.
No, the same thing, right? So it just so this guy acts here. I'm then taking the quotient with respect to that. Just quotienting out the action of this.
Oh, I see.
That's all. Yeah. I'm just so not. I can't quotient the whole thing, but quotienting is some subalgebra action of that. Okay. So this is the conformal block for me.
It should contain the information about the size of complex structure, right?
Yeah, because already there. It's a stable curve. Yeah. Okay, so this is my conformal block, and then it has fabulous properties. And
so this is like the space of conformal blocks of the torus, for instance, right?
yes.
If C was a torus, this would be the space of.
Yeah. So
There you could think of without any punctures also, right?
Yes.
yes,
So
there.
if you
Yeah, but then there's this some propagation principle that you can assume the punctures are there. So
no, but if I want to just consider space of conformal blocks.
yeah, you just put 0 here. That's all. Or the representation has to be 0. Yeah.
Oh.
The vacuum representations.
Even in the sphere with some number of punctures, if you take dimensionality of the space of conformal blocks, that should reduce to the number of singlets as representations of origin minimum.
Yeah. I mean,
So that is also very easy to see from here or something. This is the space of conformal blocks, so you can ask about the dimensionality.
but there's a Verlinde formula that computes the dimension.
Right. So that is like for the representation of Wilson lines, and here this is the same. This space dimensionality of this should be the same, and this is.
Yeah, I don't know how to compute it independently without the Verlinde type formulas. I mean, in some cases I can compute it, like the 3-point case I can do it, but not in the even like if you just take the Verlinde formula, okay?
The fact that this dimensionality is given by the Verlinde formula, this
Yeah.
is the question for me.
Yes, it is because it's isomorphic to that space. How can it be two different spaces not have a different formula? If you have two different, it's spaces are isomorphic. Of course, they are given by the same formula.
This is the part of the proof, right? That the dimensionality of this.
No, the dimensionality of the proof that doesn't come in the proof at all. It's just purely representation theory.
So it says you are given, let's say, in number of insertions on sphere. With
Yeah.
every one of them has some representation.
Yeah.
considered in it.
Yeah.
So you can ask what is the how many singlets of Kac Moody algebra that you can have with this Wilson lines.
Yeah.
That has some answer which will be given by Verlinde formula.
Yeah.
Now you can ask the question that given these points, how many conformal blocks I have, which is what is the dimensionality of the space of conformal blocks.
No, but I think
Yes,
that
obviously
count
same.
cannot. I don't think this count can be equated to the Verlinde formula count very easily. That count just not. It's so I think what your equivalent question is the following: you take the Verlinde formula. There's a level there, right? Always the L. Let that level rise high up. Is it easy to?
High up then it's sort of.
No, but not from the Verlinde formula. It's not very clear how that thing depends upon L or not. Not at all clear.
Right.
So I think the same problem will happen in this part also. You try to compare the singlets with the Verlinde formula. You learn it the same type of problems. Okay, so let me jot down some properties of this. So these things, if you take moduli space of curves with n mark points and take the compactifications, so V lambda G L of C.
Sorry, I just one quick question.
Yeah.
In your previous thing, the part you just dropped out,
Yeah.
you're keeping track of the Z dependence also.
Yeah. Because that's,
Here you're not keeping track of it.
no, because the curve, right? Curve and a mine.
But in your notation, there was no Zs.
Yes,
Why?
sure. Yeah. So you could probably Sure. Yeah. Curve minus mark points. Yeah. You're right.
Is there any canonical choice of basis for this vector space?
No.
For this space of conformal blocks?
No.
No.
There's no choice for precise representation theory also in this.
Right, but if there is something very canonical, that is very helpful.
Okay, so this V lambdas give a vector bundle on MGN bar. So as I mean that you remove the C's and the P's in MGN. Okay. So V lambda. So vector bundle. I will denote the vector bundle by bold. Bold GL. Bold GL. and these vector bundles have a flat, so V lambdas GL restricted to the smooth part carry a flat projective connection. Okay, so this is known as the WZW, or the Hitchin connection. So this comes from the Sugawara construction. Okay, so this is a Virasoro operator, and then Virasoro operators by the Sugawara construction acts on these guys, and this action gives you the connection. And the Tecmuller space, you're going to think of the Tecmuller space up to quotient by the mapping class group. Yes, so I'm saying that, so this V lambdas, right, was defined for one particular C and one particular choice of a point. Now if you move them,
That's a point in the
Tecmuller space. Now if you move them in the Tecmuller space, they give you a vector bundle. And then the vector bundle restricted to the smooth part, like the interior, it carries a flat projective connection. This is the WZW. This is the WZW connection. Right? Yeah, this is the monodromy matrices. So yeah, in the genus 0 situation, you get back the KZ equations.
Flat? So
Huh?
It is a flat connection?
Flat projective. Yeah, it's a.
So if I am understanding right, so I have this conformal blocks labeled by J's, and then I'm changing these Z's and moving
Yeah.
by changing Z's.
Yeah.
And say I am making a loop. So
Yeah.
and then when I come back, I'll multiply in simulations. I'll multiply my basis of conformal blocks,
Yeah.
and because I have moved in a curve.
Yeah.
And this the quantity that I will multiply with is this.
Is some PGLN of this of that fiber.
Curvature is only at the insertion point.
Yeah.
Where he's saying in the smooth part it's flat.
Yeah, the smooth part. Yeah, but on the other side, you get into singularities. There's not even a connection. Okay, and
What is that word
which word?
after V?
Carry a flat projective connection. Yeah. Right. This is the Hitchin connection. Yeah, we know, but only in some special cases because.
Yeah, it's like it just
Okay, and so this has some. Yeah, so this has some properties. The property is the following. So if I take a nodal curve, okay, and I take the normalization of the curve. So think, right. So you have a, I mean, if you have like a, so if you want to think of this in this way, so if you have like a look at the Riemann surface and you take a curve and you are pinching the curve, right? So that will give you something like this. But then you can just cut the curve out, right? That will give you two more. If I cut it out, that would give you two more boundary components like mark points. So that will give you something like this, the normalization, right? So there's a fundamental relation that relates conformal blocks on the nodal curve with the conformal blocks on the normalized curve. So
This is how the curve, if I draw the curve on these diagrams, and after the curve it's going to look like this.
yeah, exactly. Yeah. So, or you can think of this. You join them, you get this, or then you pinch.
Well, I'm sorry, I didn't understand. This thing is a boundary.
No, yeah, you can think of them as like so there you can think of Riemann surface with mark points, right? As in the equivalently as Riemann surface with boundary, right? Because you can cut a disk around the mark points. Yeah, and this thing is obtained by this collapsing this cycle, whereas this thing is obtained by cutting out the thing. So that's why
Are you going to a particular point in the corner of the Tecmuller space?
you can go to any corner more or less. Yeah. So just this is like the generic picture. So then the theorem is the following. So let me call this curve C, and then this called C tilde. So C, this is isomorphic to the direct sum of VG L C tilde, but you have to be careful. So there are two extra points, right? The points that get identified, right? Here, those things. So there you have to add stuff, the insertions in G. Okay, and finally, which is I guess this in the physics literature is called, I think is the fact that the Chern-Simons theory or dimension 3 is identified with the WZW for the Riemann surface. So if you take one G of C, okay, so G is the simply connected group with Lie algebra G, and if you look into the bundles G bundles on C, this is a moduli stack, or you can think of it as a symplectic manifold. there is a pre-quantum line bundle. Okay, so because the Picard group is this, there is not much choice going on, and the H naught of those things is isomorphic to dual. Okay, so I think I'll put to 0. Dual of the Lie algebra G and the curve C.
I'm sorry, just going back there.
Yeah.
Suppose you had, it's like you're putting some of your insertions on one side and some on the other,
Yeah.
and then fusing, right?
Yeah.
Now, the side where you put could have had a smaller genus than this
Yeah.
whole thing.
Yeah.
So that's all in that notation.
Yes. Because this thing is in here, right? Because
Right.
I put the curve C tilde, and when you normalize, it can be disconnected also.
Yeah, because you're thinking of the whole thing.
Yeah, I'm thinking of the whole thing. Yeah.
Moduli space of the
Yeah. So in terms of this, I think.
operator as algebra surface.
Yeah. So I think I should write it like this. There's a map from G1 cross G2 to N2 plus 1 going inside G1 plus G2 to N1 plus N2, and ask how the vector bundle splits. So you take the vector bundle here and you restrict, and this splits as this formula. So that's the whole statement.
So this 3 is what in string theory is called the plumbing fixture?
Yeah, I think so. Yeah,
So what is plumbing fixture? What is
this 3.
3 point?
Yeah, what's the plumbing construction? Yeah, and then this, I guess this should be called the Chern-Simons WZW correspondence.
So the left hand see somehow is the left hand side is somehow Chern-Simons theory.
Yeah, I don't know how, but I guess this is a symplectic manifold, and you have pre-quantum line bundle, and you take states of the quantization. Yeah, this Chern-Simons theory. Yeah, the quantization of a moduli space. Yeah, it's like Chern-Simons theory for the Riemann surface cross R. I think that's what I have read the stories about.
This is which is
Yeah. Well, okay.
no idea.
Could you explain this BM once again? Sorry.
Which one?
BM.
No, bun. So bun is like G bundles on the curve, right?
Oh, G1.
And then you take all possible G bundles on the curve up to some equivalence, and that's a symplectic manifold. And then this is with the Picard group Z. So the symplectic form is only the Picard. Since the Picard group is Z, there is not much choice. And then take this line bundle, which has whose curvature form is that symplectic form, and then you take powers of
And
it.
that's why it's not into this BM.
This conformal block, yeah. So somehow this, yeah,
What is this star mean?
start the dual. This dual.
Okay, dual.
The vector space dual, yeah. I should put it. This, okay.
In higher genus surfaces, you can carve it in a say you have let's say genus 2 surface.
Yeah.
You have some number of operators
Yeah.
inside, you can carve it in different
Different ways, yeah.
different channels
And then you get different versions of this decomposition, yeah.
different version of this
Yeah.
decomposition. And this V lambda does not refer to any particular channel. This is a collection of all possible ways of cutting.
Which one?
This V lambda that you have written fixed.
The V lambda is just the conformal block, right? The V lambda is just this one. With the full thing.
Different.
Yeah. Yeah, so this thing will not depend upon the way you cut. Yeah.
It's like 4-point function on the sphere. You can
Yeah.
fuse these guys.
Yeah, confuse the two guys. So both give the same answer.
Right. So the number of conformal blocks will not change.
Will not change.
Yeah.
But the functions itself, the base as a even the space will be isomorphic.
It's the same. It's just different bases.
Okay. Yeah. So any other questions? Sorry.
And this is true for any even real dimensions. Last point 4.
For
The argument, I mean, this 3 is from the diagram, it seems like it's on a 2-dimensional Riemann surface, but 4 is true for any complex manifold.
no, because these things are not defined for only for Riemann surfaces.
Okay, so this is N2.
Everything is in dimension Riemann surface. Yeah. Riemann surface. Okay. So yeah. So let me tell now how the rank level duality comes into the picture.
That is a vector. We have used 1 and 4 instead of 1 and 4.
Yeah. Okay. So now how does set up rank level duality questions, or like the previous question that I initially started in this picture? So let's come up. So let's come up with something. Some notion. So if you have a Lie algebra G1 mapping inside G, okay, right? You take the corresponding map between the Kac Moody algebras. Okay. So now if you take a representation up here, H lambda of G hat, okay, So then you can ask, okay, if I restrict up here, down here, how many components do I get? Because the category is semi-simple, everything is irreducible and so on. So, but these things are infinite dimensional, right? So the number of components I can get can become infinite.
I didn't understand the question. Could you please?
So take a sub-algebra, okay? So G1 and G2,
Okay.
okay? So given a map of Lie algebras, you can extend it to the map of the Kac Moody algebras, where the central charge here gets multiplied by the Dynkin index. So then you take a representation up here,
Yes.
and you restrict as a representation here. Now the question is, how many components does it decompose? Because I know what is the integrable representation.
How many different irreducible
How many different irreducible representation? First question is the list finite?
Yeah.
Okay, the list is not finite, but there comes the class of embeddings called conformal embeddings. So conformal embeddings. Okay, so conformal embeddings tells you the so it's a condition on the it's just a numerical equality. So let me and you guys will like it. So let's say of Dynkin index D. So D times the dimension of G1 times the D plus the dual Coxeton number So this equality is known as conformal embedding. So it says that the central charge of this equals the central charge of this. Okay. So as I was saying that this is a flat projective connection, right? So these are the projective connections have a central charge. So these are the central charges in the theory. Okay. So this is equivalent to saying that for all lambda in P1 of G, the decompositions of H lambda to G1 hat has finite number of components, and this is also equivalent to saying that the Virasoro operators of G1 hat at level D is same as the Virasoro operators of G at level 1. So these are all equivalent statements. So you can central charges are getting controlled, and that enough to control the Lie algebra, and that is enough to control the decomposition.
That was 1 or L in that equation?
Here?
Above and above.
Huh?
Above. So the equivalent.
Yeah.
1 or L?
1.
And D is what?
D is the Dynkin index. It's the ratio of the killing forms. So you can think of this as, so the fundamental group of this is Z and the fundamental group of this is Z. So it is the map the generator goes to.
Actually, I didn't understand this part. Can I ask you?
Yeah, sure.
Suppose you had SU3 at level 5.
Yeah.
And you want to now look at SU2 subgroups.
Yeah.
This is the kind of thing.
Yeah. So I'm coming to examples. Yeah.
You're coming to that.
Okay. Yeah. So yeah. So okay. So what are examples? So there are
What is going to be G2?
G2.
The thing that is dual to that. This I should think as.
Yeah, but G could be semi-simple. Yeah. So G is simple, but G1 could be semi-simple. Semi-simple embeds into simple, right?
Yeah, but when you say level rank duality.
Yeah.
You will say
So this
that
will be the level 1 guy, but then this is
NK.
semi-simple.
NK,
I
exactly.
did do
SU and
SU.
Yeah. So yeah. So G1 could be semi-simple. Yeah.
And this was also P1 of 1, the line that you wrote, it was P1?
P1, yeah. It only happens at level 1. This equal.
Right. So if you replace this 1 by L, would it be P1?
No, it is only no. So if you try to do this thing, okay. Okay, this equality is only satisfied while k equal to 1. This was proved by Kac. So you cannot get anything else for k equal to 1.
G needs to be of level 1.
G needs to be of level 1, yeah.
And then you are saying this is equivalent to saying that when you decompose the representation into
The list is finite.
the list is finite.
And this is also equivalent to saying that the Virasoro actions are the same.
Some
This is asymptotic of the branching function more or less. Because there is a character formula to compute the characters, and then
Should be related to some Sugawara statement.
no, this is the Sugawara statement coming here. Yeah.
Could you explain, please? If you don't
No,
mind.
so sure.
So you start with a higher group at level 1. And
Yeah.
what is going on now? You're taking a
So
sum.
now, yeah, you're taking SU. So let's say, I think that's what you will say perhaps.
Yeah, so maybe can you like give me 5 minutes? Okay. So maybe examples. So okay. SLM direct sum SLN going inside SLMN. Okay. So then SOP plus SOQ going inside SOPQ. Okay. So then I would put SOP inside SLP. Okay. So these are examples. 2, 3. So SP2R direct sum SP2S going inside SO4RS. Okay. And number 5 is this one. So SU2 inside SU3, right? Because SU2 is SO3, and then SO3 goes inside SO3. I put SO. And then finally this is G2 cross F4 inside E8. E8. Okay.
What I didn't understand that.
Yeah.
What is that?
Oh, D is the Dinkin index. So it's the ratio of the killing forms, right? Or you can think of this as follows. Okay. So if D is D is semi-simple, G1 is semi-simple, right? It will be 2 numbers. So if you look into the group, right? The group is simply connected. So the third fundamental group is Z, right? If you have a map between the groups, that will induce a map between the homologies, and it's the ratio of the homologies the Z's goes to.
In your first example, D will be N or N. Right?
Yes. So that's what I'm going to write now.
So D is the level of the guy when the level of the above guy is 1.
Yeah. So
how much is the embeddings?
yeah. So A is the ratio of the killing forms. So
If you allow me, the first one is saying that if you have a theory of Mn fermions, and you look at it as just as SUM is then there are N flavors.
yeah.
Or N flavors.
Yeah. So let me write down the Dinkin index up here. So this is Mn. Okay. This is QP. This is 2. This is SR. This is I think 4, and this is 1 and 1.
These are all of them?
No, there's a complete list. I mean, I'm not. So there's sub list. There's some finite list. So this has been classified by works of Schillekens and Werner, and also by Bayes and Buchnet. They have classified all. So they have classified the list of conformal embeddings
For semi-simple Lie algebra.
for semi-simple Lie algebras. Yeah.
And these results are important, first of all, because you said that there is a finite number of them.
Yeah.
This is one of the
Yeah.
And second one is also, I don't know if it is a general theory about affine Lie algebras. At least for compact Lie algebras, there is a statement that if you take direct product, you can always reduce it into direct sums.
Yeah, that's true.
That is a
But this is not a direct product though. Yeah.
Right, it's also not.
No, it's not true.
affine Lie algebra.
Yeah, but for direct product, this is not true.
Is there a theorem like that?
No, it's false. It's false. Yeah.
So this is also another content that you can direct.
This is a if and only if. That's what I'm saying. It's both directions true.
What is your question? If you have.
No, what he's saying is that take the diagonal embedding G to G cross G, right? But and then if you do finite dimensional representation, this is the tensor product representation, right? But in here, right? If you
Here this statement is
no,
probably not true.
no for affine
So
Kac Moody
this is
Lie.
also a content of this statement.
Yes, because that's what the if and only if statement, right?
And so just to
Yeah.
make sure, in the first example, Y1 could be either HM, SLN or SNN.
No, which one? G1.
Oh, this
Oh.
G1, sorry, G1, yes. The sum.
No, G1 will be the sum. So will be the sum. So if you want to see, yeah. So I think
Phrasing it in a.
I'm phrasing it in a dubious language. So if you want me,
Yeah.
I could.
So it's level right? We call it.
Yeah, I probably should.
But in the third line, for example, this language is better.
Yeah. So I should probably.
Yeah, that's what I was.
Okay, yeah. I'm
So
sorry
what
about that.
does it mean? The third line, what would you say is level right role? Third example.
Third example, yeah, we'll come to it. Yeah.
Okay.
Oh, it's just some weird. No, because the thing is, okay, one statement result, we'll see what the result is. Okay, so maybe, okay, I think
This one, you have time.
you have time. Okay, that's very good. Yeah. Okay. Yeah, Tanmay, I'm not sure if you.
I'm really sorry, but
Yeah.
can you say that the central charge, the sum of the two central charges is equal to the parent central charge?
Yeah.
I thought, shouldn't it have been that either one of the two central charges was equal?
No. Well, the central charge of a semi-simple is the sum, right?
Because I'm thinking of one as gauge and the other as gauge. I'm thinking. I'm thinking of Mn fermions as a collection of M tuples of L fermions.
Yeah.
So that L fermions is has.
No, but that theory has SUM symmetry as well as SUN symmetry.
But-
so you should take into account the central charge coming from those currents as well as those currents.
But I'm taking into account only from level. So I'm thinking of the L fermions as SUL theory, and then the fact that you have M of those is level M.
Yeah.
That should account for the whole thing.
No. We just took into account the contribution of one chiral symmetry. This theory has two chiral symmetries, right? There is an SUL symmetry that will also have sort of its own sort of.
Yeah, so what you are saying, I think, is the following, right? So if you have the, so I think that chiral symmetry, I think there's a, so this center of this thing, right, is Z mod Mn, right?
That's some.
Right? But that gets contributions from both of them, so not one.
Suppose if I instead of making both the SUs,
Yeah.
if there's some U business, will
Ye-
it become nicer?
Yeah, it becomes nicer, the statement becomes nicer, but the problem is that when you're doing conformal blocks in the Lie algebra language, that's a reductive Lie algebra corresponding, but it's compared to semi-simple, and that's where things go bad for.
Okay, thank you.
Yeah, okay, so this is the statement, okay,
I get it.
so,
When you choose G1 in G,
yeah,
you are supposed to, you can choose any sub-algebra of that Lie algebra?
Yeah,
Choose any sub-algebra.
yeah, any subalgebra that satisfies this condition, yeah,
And then say I have chosen G1, which
Yeah.
is a sub-algebra of G.
yeah,
And then I am asking this question. So D1 is supposed to be some ratio of linking index for G1.
yeah,
What about D2?
the other one,
What
ratio-
The other one is like
G2,
orthogonal
right?
decomposition?
no, but, so I mean, so you have
What
a,
is D2
inside G, right?
right? What is this arrow? Is this like equal sign or is it like orthogonal decomposition with respect to y?
Which arrow?
This arrow, yes.
Yeah, is a sub injection, right?
So this is supposed to be an injection.
Yeah,
Okay.
like here,
Okay. So that defines what G2 is.
yeah, so,
With G1, I want it to be injection, so that.
yeah, everything is, it's restricted to the sub thing, so yeah, so for any injective map you have a Dynkin index. Okay, so,
I'm
Yeah.
just confused over something.
yeah, sure,
So if I have a resonated model of G1 times G2, capital G1 times G2,
Yeah.
algebra is small G1 times
Yeah.
G2.
Yeah.
So what usually we do is that if we want to calculate the full central charge, we just take the central charges of the small G1s and the small G2s, and that's give me the full.
yeah, that's what I'm doing
This
here.
is exactly the statement because
Yeah.
I don't see the dimensions get matched, right?
Which one?
On the right hand side, let's say take the example 1.
Yeah, it should match, I
Example
mean,
one, the dimension is mn squared minus 1.
yeah, but then there's this quotient that is completely non-trivial, right? Because these dual Coxeter numbers that come up.
So you're saying you're expecting dimensions to add up?
No, the dimensions never add
They
up.
don't add up,
No,
but-
they don't add up.
No, but in Wisdom-innovated model, if we have G1 cross G2,
Yeah.
when you calculate the central charge of G1 plus central charge of G2, that's the central charge of the full plane.
Yeah, that's what this statement is.
Yeah. Right.
The central charge doesn't have the dimension, it also dimension modulo these guys.
The G is not a semi-simple. G is simple here.
Yeah.
I mean, what you are doing, G1 at level K1 and G2 at level K2. Of course, the central charge, whole theory would be the sum of central charges together.
Right.
But here is the additional statement. There is a G1 at level K1, G2 at level K2. This is equivalent to G at
Level K.
In fact, K is 1.
K is 1.
Okay.
Yeah, so this is the central charge, right? Not the dimension. So dimensions in here, none of them the dimensions add up.
So why does K need to be 1? Is it some
Oh, it's just some numerical inequality. If we just, so this Dynkin more or less classified all the subalgebras, right?
This is fermions. Fermions of K equals. One fermion is K equals, I think.
Okay, yeah, that's a good. That's a clear like must be a.
The right hand side is always K equal to.
Yeah, right hand side is always K equal to 1.
Okay, now I think I get it. Yeah.
Yeah.
Okay. Right.
Okay. So now let me formulate.
One thing is K equals.
Now let me formulate the.
Break it up in different ways.
Yeah. So
And your Mn is the level of what is
It's Mn fermion. So Mn is the level. I mean, Mn is the rank.
Mn is the rank plus 1.
Rank at level 1. Because
Yeah.
two fermions at level 1.
So your Mn depends on each of
Yeah, right. That's at least a simple example.
Yeah, that I
Yeah.
agree
you have free fermions.
Okay, I'll say it quickly, but we should let it go. But suppose you have Mn free fermions. You can think of it as SUMN or UMN, from the UMN theory at level 1. But you can also break it up and think of it as UM theory, but n flavors of that. So just n different copies of that. So UM theory at level K, or UK theory at level M. These are basically the same thing. They're all the same as the original.
Yeah.
Roughly that's what it is.
Yeah. So now let me formulate the question. Okay. Yeah.
Is there an example where the semi-simple subgroup has 3 factors?
There is, yeah. So in E, I think there is something in E6, and then it's like probably SU2 3 copies, maybe something like that. Yeah, I can forward you the list. I mean, yeah. Okay. Yeah. So let me try to get back. So the question one formulates is the following. So yeah. So then okay. So how does the map comes up, right? So I want to use this fact. Okay. So let's say I am taking lambda in P1 of G, and then this splits up. So I'm just going to consider the cases where consider the cases where these things are semi-simple. Okay, where there are 2 different type of statements one is expecting. Okay, so in the same, if G1 is of the form G1 is semi-simple. So then this thing split up as this. Okay, I'm just ignoring the multiplicity. I'm assuming that the multiplicity is 1. Okay, it's not always true, but in all these cases it's true. So then I can do the following, right? So lambda mu in the set, in some finite set, right? So conformal embedding guarantees me that the set is finite.
So the h lambda is the module of 1 and the
Yeah, the h lambda is the module of one, and this is the module of the other. Okay. So then I can do the following. So I can choose vec lambda 1 up to lambda n. Okay, in P1 of the bigger Lie algebra. Okay, I choose lambda this thing and mu this thing in P of the whatever the level, the Dinkin index, and then this such that lambda mu is in this with the appropriate index. Okay, so choose n tuples of level 1 weights and then choose something in that appears in the branching rule, right? Then you get get maps of the following form: tensor product of h lambda 1 to mu 1 to h lambda I tensor product I equal to 1 to n.
And sorry, did you say it was unique that one representation then gave a single representation?
Not always true. So for example, not always true.
Not
yeah,
always?
not always
In
true.
Example 1, is it true?
In my example 1, it is true because if you fix the 2, the other 3 is fixed, but not in these cases, and so.
Fine.
Fine.
But focusing on level 1, you can fix that and you give me both of them.
Yeah, exactly.
So
Exactly.
sum contains only one entry you are saying?
No. What I'm saying is that if I fix this and fix this, there's exactly one that appears.
Is that what you were asking?
No, I was asking something else.
Oh, what? Sorry, what were you
So
asking?
there's only one there, right?
Yeah, there was only one.
No. There's more. More. So for example, like I'll just deviate a bit. So if I take this as the fundamental representation, okay. So for example, if I see all these things have the finite dimensional representation sitting inside, right? So
Yeah, it's obvious. Sorry, thank you.
yeah. So this thing splits up as
Yeah, thank you.
omega of this.
Thank you.
So direct sum.
Yeah.
over lambda. So that always there. Okay, so you have a map between this. So this will induce a map between the conformal blocks, right? Because you can take in co-invariants. So this I get a map between the conformal blocks. So it's an arbitrary genus. There is no problem.
Sorry, just one more. So you're saying this sum will only be finite if and only if this
The embedding is conformal. Yeah. So you have a map between this. Sorry. Yeah, sorry. The notation is a bit complicated, but I guess it's like the festival time. So it's festival of notations. So yeah. Okay. So now I'm in a good shape. So here. Okay. So this is the format, right? Okay. So now let me give you examples of some branching rules that show up.
This map.
Yeah, go on.
What about the existence of this map? It's only when you have this mapping conformal. Right?
You can exist and the map always exists, right? But the problem is the following. So what is good in here is the following. So I have just erase something, right? The central charges are equal, right? So you have the WZW connection here and you have WZW connection here. They commute. Okay? So the central charges are equal. So the map is flat with respect to connection. So if you want to prove it for some statement of some particular curve, right? Then it holds for any curve in the neighborhood because the rank is always constant under a projective connection. So that's very important for me. Yeah.
So if we just think in terms of square matrices, there are some two blocks separated from each other.
Yeah, you can see.
Some sort of.
Yeah, man.
That's why, because you made the comment of commuting, the connection being commuted.
Yeah, but this is a general fact that if you have a map of vector bundles,
Okay.
I have a which commutes with the connection, the rank is constant. It's so because the covariant derivative, you can just take that.
Sorry, the last equation, could you say it in words, please?
Yeah, sure. So I mean, so you can take this guy, right?
So
No.
you're taking a vertex operator, which is in the representation lambda.
Lambda. Then but then by definition, this is a quotient of this guy, right?
Okay.
But the quotient by G1 cross G sits inside G, right?
This bunch of vector operators where
Bunch of vertex
this is
operators.
a
Yeah.
conformal blocks,
Block.
space of conformal
Yeah.
blocks of one.
So maybe write it.
G1 factor, the G2 factor.
Each point has a G1 and a G2 factor.
Yeah. So this one has a G1 factor, this is a G2 factor, but the G1
and
directs
each
some
point.
G2. Yeah. And the
Okay.
G1 directs some G2 goes inside the G factor.
Yeah, and so this is one of the representations that appeared inside
Yeah.
lambda there.
Right, exactly. That's what the note.
Anyone.
Anyone, choose anyone.
Okay, fine. And what are you saying about
So yeah, so this is a format, right?
this format?
Now one can ask the following question. So this is also for curves of any genus, and then you can extend it to a vector bundle, and then if you want to go it to MG n bar, there are some corrections you need to
You're saying consider this object.
consider this
Say
object.
something about it.
Yeah. So then question is the following. If dimension of this thing, the big guy, is 1, okay, or if S is a canonical object, so canonical object in this is the induced pairing perfect. So this is ignore this line, but if this is C, there is a pairing, right? And the question is this pairing perfect? It's a non-degenerate pairing. All right.
Dimension of that, so that's a trivial kind of thing.
Yeah, so that's a C, but it could have non-trivial monodromy. But the question is this a perfect pairing? That's the. Yeah, means the bilinear form is non-degenerate because this is a vector space, right? So you have two vector spaces mapping into C. It's a bilinear form, and asking if the bilinear form is non-degenerate, right? If the bilinear form is non-degenerate, so if true, so
There
this
are no other products, and that's what you have, right? That's the only way you can write it.
that's like the natural way.
One factorization.
Yeah, only one. So then that would imply that the conformal block for G, right, at C at level D1 is dual, like sort of projectively dual to the conformal block of C to D2.
But why are you saying that dimension of B lambda is 1? Where did that condition come from?
No, because otherwise you not get a pairing. That's all.
Level is 1 on G.
Yeah.
So that's
Well, I mean it's more or less never true, but in higher genus, no. So yeah, come to that.
for spheres.
For spheres, there is a lot of examples in many cases, except like for type C, there is one dimensional. For type E8, in any genus, it's one dimensional.
But you
Okay.
want that pairing to exist always, right? Not only when.
Yeah, but then I cannot talk about non-degeneracy, right? It's not a pairing, right? Because unless it's C. Okay, so that's why I'm saying that if the S is a special section, right? If you have a special object, right? Then it will induce a map between the duals of this, right? So that's the general form. If you have a special object, then you have a map between the duals, and I'll ask that if that map is an isomorphism. No, so special means that sometimes because there is these identifications of various things in geometry, right? In geometry, there are some canonical like theta sections and so on. Like, so there are some canonical sections in geometry, coming from the geometric language. So that's, I will call that special.
Does that mean in this case that there's no monodromy of the full operator?
Which case?
In the case that this
Yeah, yeah. So
that one-
it's saying that it's saying that it's preserved by the monodromy. So what it says that
monodromy is a pure phase.
yeah. So it's saying that the canonical object is the monodromy preserves the canonical object. So it's a projectively flat section. Let's call it this way. This way. So this is the
For dimensions greater than 1, this question doesn't even add.
no. If the dimension is greater than 1, you can ask if there is a special section S which is preserved by the connection, and then I can ask the same question.
I
If
mean,
they say to one.
physically you want the answer always, right?
Yeah.
Because you want to say that this theory, the blocks of that theory and the blocks of that theory are related.
Yes. So on
They
P1.
only work in special cases.
Yeah, but in P1, but not the blocks though, because the primary states are never in bijection. It's the coset construction that will give you the isomorphism, not the. I think it's the coset conformal field theory is isomorphic, not the actual conformal field theory, because the primary states are not bijective, if I'm saying the correct language. Yeah.
In conformal field theory, then what is S basically?
Huh? What is?
What is S? The small s that you wrote.
Oh, that's the whole thing, because the small s only exists in algebraic geometry. So in conformal field theory,
Yeah.
it usually doesn't have any. I don't know. So I don't know conformal field theory, but the saying the Lie algebra language, it's not at all tractable object. That's the whole. That's the one.
That's coming from the variety that.
That's coming from the Bun G varieties, and then the description of the line bundles and so on. So it's like a very geometric object that has no interpretation and representation theory. That's the problem. Okay, so now let me tell the results. Okay, so let me have those results. Okay, so any other questions on the form on the?
Sorry. When this dimensionality is 1,
Yeah.
I wanted to understand what you can say about the monodromy of this block and that.
So there's just because the map is flat, the projectively flat. So the monodromies are projectively equivalent.
Projective, but it's not saying. Are you saying that you're going to get the same phase when you go one round?
Yes, projectively.
I don't understand.
No, so as PGLN representations, they are
Meaning they're
isomorphic.
pure phases.
Yeah.
That the phase. See, because the right hand side is just a pure phase.
Yeah.
All the matrix part of the monodromies have to sort of cancel.
Yeah.
Should be the inverse matrix or something.
But
No,
that's
but the
pure
inverse.
phase.
No, but the inverse metric. But this map is only projectively flat, which means there is a scalar factor that's
Phase.
Yeah, the phase. Yeah, exactly. Yeah. So up to phase, they are the
Yes.
same. Yeah.
Okay.
Up to phase, they are the same. So that's why I'm saying if you take PGL,
Yeah.
then you are killing the phase, right? I mean,
Right.
okay.
No, but even the phase should match up, right? Or not?
Yeah, I think this is this USU business. You know, level line duality is only precise when one of the factors is U.
Yeah. Okay. So, but
If you want it out by the phase, then you get exactly equality.
yeah, what?
Yeah, but that's not good enough for this.
Yeah. Because it can't just information.
Yeah, this is lambda is some very specific representation that you have given.
You can choose.
It says you have chosen some representation.
Yeah.
The fact that this dimensionality will be 1, it is a constant on C. It is a constant on
On lambda, on C,
Yeah, so
on the number of points. Yeah.
right. So
On
say-
everything.
Say number of points is given
Yeah.
and say C is given.
Yeah.
Then it will be a constant on lambda.
Yeah.
I'm just trying to
Yeah,
understand
yeah,
what the
yeah,
constant is.
Yeah. It
So
could consider on
then
lambda.
there might or might not exist a lambda for which this is
Yeah.
1.
Sure.
You're only making statements in the case that this pairing
Yeah.
descends from a lambda
From-
where that thing was.
And then for P1 there are lots of examples. That's what I'm saying. If you have a sphere, there are lots of examples.
If you are a sphere,
Yeah, there are lots of
number
examples.
of points is
Number of points could be anything.
could be anything.
Yeah,
then
there are lots of
There
examples.
are a lot of examples in which this is 1.
Yeah.
So P1 always happens to be lambda I transpose.
Yeah. So I'm going to. So now I'm going to come to the examples. Okay. So yeah. Yeah. Okay. Okay. So let me go by one. So maintain the same number. So this is due to Nakanishi-Tsuchiya. So the geometric version of this theorem in Highlight genus is due to Belkale, and also by so I also proved so I mean there are some statements in Nakanishi-Tsuchiya about which are not very clear, so I had to add some stuff there. Okay, so the theorem is the following. So saying that theorem is saying that that if I take lambda to be omega I1 up to omega in, such that such that such that Mn divides summation ij j equal to 1 to n. So this guarantees that the dimension of the conformal block is 1. Okay, then so then 1. So then this. So then so let me call this pairing part. So call this RL. Call this then RL is an isomorphism. Isomorphism. And then so the lambdas here are Young diagrams. You can take them, and mu's are transpose. That's some set of it. But then there is a center here, right? The SUM. The center acts on these things, and then the center here. So you take these guys, and then you act on both sides by the center.
This is the U1.
Yeah, this is the U1 action. That's where it comes from, and it spreads out. So okay, and let me make a brief comment, and I'm not going to write, because so as I point out, as L goes to very large, then it becomes equal to that first duality that I wrote, and this duality can also be seen in another way. So there is a theorem of Witten saying that the quantum cohomology of the Grassmannian is isomorphic to the fusion ring in type A. Okay, since I have said that the two Grassmannians are isomorphic, the quantum cohomologies are isomorphic. So the structure constants for the quantum cohomologies, right, should be isomorphic. And if you just evaluate it on the fusion ring, you get these guys. I don't want to answer a question on this. I want to finish first. Okay. So theorem 2, the same holds for the. So no, I want to go with theorem 4 first. So theorem 4, this is due to Takeshi Abe. So he's saying that if you take lambda to be the spin representations, so spin plus minus, such that so plus minus 1, such that the sum is even. And so like you don't have to. So the sum is like a positive sign. Then V lambda of sp2r at level S is dual to V lambda transpose complement of sp 2s at level R. So this because you have a Young diagram, right? Okay, RS type. You can take the complement and then take the transpose of the Young diagram. So that's this correspondence. And then this was extended by myself to the case when lambda is of the form either zeros, a bunch of zeros and the vacuum representations. There then it is just this SPR at level S. These are different versions, yeah. So this is yeah. So I think right.
Depending on what your lambda was.
Yeah. So
Lambda is dual to lambda transpose complement
or the other one. So the reason is this because yeah, again you can interpret this as the action of the primary, the central current U1 action because it's on Z mod 2, or you can think of this as the following. So this construction, okay, of the modules of the highest weight vectors is in the Ramond sector, and this one is in the Nevio-Schwarz sector. I think there's a correspondence between those that brings this up. But this is all I've been explained. I don't. I'm just copying words from other people. Okay. Yeah. This is a statement on. No, this actually holds in an arbitrary genus. C. Yeah. So C is smooth of any genus. Yeah, this is on P. Yeah, the first one is on P1. Holds for no. This statement is for P1, but then there's a similar statement by Belkale in higher genus. Yeah.
And when you say the isomorphic, that includes the monodromy.
Yeah, isomorphism includes the monodromy. Yeah, that's because that's part of the map, right? Okay, so number.
The second statement also on general synthesis.
Yeah, because you can.
And what about the fact that there's an inverse matrix? That doesn't matter. That the monodromy matrix of one has to be the inverse of the other. You continue to call that isomorphic?
Yeah. Not inverse, the dual, right? There's a dual, right? There's a dual here.
I was thinking that the monodromy on the right hand side,
Yeah.
your thing was trivial.
Yeah.
So here you get a matrix, here it must be the inverse matrix for it to work.
Yeah.
So that
Yeah, but that's probably
that's what you mean. By
yeah, that's probably is coming up here, right? Because the dual, a dual of that. There's a dual.
I see.
There's a dual, yeah. Okay, so this.
By any chance somehow related to S duality? Because it maps the.
Yeah, that discussion will take some time. Let me finish first. I mean, yeah, okay. Okay, let me go with 6 first.
So why is this not valid for general genus?
Which one? No, this thing is valid for general genus, but the statements have to be carefully crafted because on one side you have SLN and the other side you have GLN in the higher genus because that's because I'm just discussing conformal law, that's why. Okay, let me come up here. Okay, so number 6, so theorem 6. This is I'll do to myself. So what we prove is that you take any number of curves and any number of mark points, any genus curve, G2 level 1 is dual to omega 4 C F4, of course mark points at level 1. Yeah, this is for any genus. Okay, and the dimension is actually quite nice. There's something to do with the Fibonacci numbers. You can write down. Yeah, I don't want the dimension, but it's a nice dimension count here. Yeah. So because here this thing is true because the dimension E8 has the conformal block has dimension 1 in arbitrary.
This statement is true only when the labels are the same. Omega 1.
Yeah, because the Dynkin levels are only 1 here.
Okay.
Yeah.
I see.
Yeah. Okay.
So 1 and 4 is just a notation. What is this? Why
Oh,
is 1 here and 4 there?
Well, because this is the first fundamental weight and this is the fourth fundamental weight, right? Because recall that you need to know what this lambdas and what the mu's are, right? Okay, so here E8 has only one primary field, and if you look into this guy, so this splits up as H0 tensor H0 direct sum H omega 1 tensor H omega 4. This is the branching rule. So this always holds. So I'm not going to write this because you can always add these things out. But yeah, this is the propagation principle, right? The propagation of Lekko. Okay, final. So this is 6. Okay, so these things are the same. Okay, right? Because because SU2 is PSO3 and so on. So let me tell you what this type of flavor is. So this is theorem 3 plus 5. So this is a theorem due to myself and Hassan Zelati. So what we prove is that, so this is the theorem which we prove is that H0 of one SO, the group SO, P, and you take the line bundle L, the square of the square of this is isomorphic to H0 of one SLP of the same line bundle of the similar line bundle in here. So the Picard group of both these things is Z. So there's a generator here, canonical generator. So you just take those canonical generators. So you're saying that the restriction map is an isomorphism. But one thing has gone wrong. It's not on the level of conformal blocks because here you have a simply connected group, and here you have a non-simply connected group. Okay. So conformal block, the Lie algebra language only works in a simply connected case. But this is very interesting because there are amplifications of these results where some orbifold conformal field theories are coming in because there are some twisted versions of these things that shows up. Okay, so that has been proved also in the same paper, but I don't know, since the notation is technical, I don't want to get into it. So this takes care of this and this. Okay, I will come back to this statement in a moment, but let me come up here. So this is the interesting case. So there, so this is a theorem, I think it's 2. So P is odd and Q is also odd. Okay. Yeah. So then SOPQ is also odd. So let's say R is of the form 2D plus 1. Or D is the Dynkin index. What's a good notation? 2M. So then you get a map like this. So I would say P1 with SOR level 2S. Oh, sorry, SOP. So 2R plus 1 level is tensor lambda transpose P1.
Can I ask one question?
Yeah.
So in particular, this isomorphism means the S matrix for one is the inverse of the other, right?
Yes. Yeah, but that's the dimension count, right? There's a dimension part. The S matrix only shows up in the dimension, right? Yeah.
No, I mean, you're defining, you're talking about a conform block on torus.
Yeah.
And this
Yeah. Right. Yeah, you're right. Yeah. So yeah. Right.
then as you go around,
Yeah.
it should
Should be cancelled by the other one. Yeah. So then this is 2S plus 1. Sorry, 2R plus 1. Right. Okay. And then this goes into some things like omega 0, bunch of omega 0s and a bunch of omega 1 in P1 setup of SO 2D plus 2M plus 1 at level 1. So this is one dimensional. So lambdas. Okay, lambda n. So lambda i's are tensor representations. So by which I mean that it integrates to the representation of the group SOR, not the spin. So I'm excluding spin representations from this list. So if I have this, then it's then this is C, and then this pairing is non-degenerate. So this is a theorem. It's in my thesis. This is a non-degenerate. So RL is non-degenerate. Okay. Now if you add spin representations, okay, so then things will go wrong in some way. So first of all, okay, this is true, and then you can always act by the central currents, like the.
So what do you can add?
No, you can change by the.
Big lambda is the same.
Yeah, the big lambda.
If big lambda you don't add spinners, then they will not appear there.
Right. So I'm going to add big lambda spinners up here. So I'm going to change them. Okay. So I'm going to add a bunch of things out here. The tensors, and then I'm adding the last two as spinners. Okay. So it's plus there's only one spin, right? So it's an odd. Okay. So this dimension. Okay. Now if you add more spinners, this dimension goes more than 1. Okay. But if you add 2 spinners, the dimension is still 1. But in that case, we showed that it's very easy to show by the Verlinde formula the dimensions of this doesn't match up. Okay. But one can show the following that in this case, so in this, so let me erase this. So in this case, what one shows is that. So let me write this as like lambda 1 up to lambda n, and then I'm putting 2 plus and minus. I will show that one proves that this is an injective map to lambda 1 transpose, lambda n transpose, and then here also you have to take transpose complement and lambda complement. Okay. Again, everything is in P1. Okay. So here it's an injective map. Okay. So one conclusion immediately you get that the projective monodromy representation is reducible. And actually I don't know what. So there's a theorem of Belkale which says that these things have a unitary metric. And then I don't know what are the other components that shows up here. That's like an interesting question for me to figure out, but I haven't been able to do it. But then the question is that, so these things, okay, it's only on P1. I don't know how to generalize this to higher genus curves. Okay, the obvious statement that you come up fails. Okay, and then there was a non-trivial statement that we came up with in a paper with Richard Wentworth and myself, where we managed to show that there exists a canonical section, and then the dimension of the two sides are equal, like the source and the target, but still it failed to be an isomorphism. There was a kernel. So and in a higher genus, right? So when you are doing this plumbing technique, right, there you have to sum over all the representations, right? There the spinors come in, and the spinors were the culprit in our calculations, and that was very clear. Okay. Finally, let me comment. Okay, so this is a question. So recently there is a
Comment. So when you bring in spinors, you're still on a Riemann surface or on a super-Riemann surface?
I'm on Riemann surface. I'm on Riemann surface. Yeah, spin representations, right? I mean,
Because okay, maybe
Yeah.
I'm missing something. Okay.
no, the spin representations.
Because, I mean, if we do this plumbing fixer in string theory, we never get spinors. If we are in Boulogne.
No, but this is not spinors. It's for spin representation. I don't know what spinors are, but the same as spin representations.
Just add them, right?
Yeah.
I don't know. I think that the more elegant way of doing is to write in superfields like super-Riemann surface.
But you don't want necessarily some symmetry between them.
Yeah. So I must mention that there's a recent paper, maybe not recent, maybe 2-3 years.
What determines this arrow and not that arrow?
Which arrow? Oh yeah. Sorry, I forgot. So there is a central action, right? Because this is a center, right? So these things are not fixed by the center. But once you have these things not fixed by the center, these things are fixed by the center. So that determines the arrow. Yeah. So there is a recent paper, not recent, maybe 2-3 years back, by Poshen and Nathan Seberg and somebody else, where they propose some things on the with spin representations. But that doesn't. I have not been able to transfer this in the language of conformal blocks as we define, or as I think. With spin representations as of rank level duality for this setup, but yeah, I haven't been able to translate that in a mathematical language. And finally, I would like to point out that there were some conjectures of Nussbaum. So Nussbaum proved that the monodromy representations of the Hitchin connection or the WZW connection on SL2. So Nussbaum's question. So you take H0 of Bahn SL2 on a curve of any genus, and then you look at level 2 guys. So you look at the monodromy of the WZW connection. So Nussbaum proved that if L is not equal to 1, 2, 4 and 8, this monodromy always have elements of infinite order, the monodromy representations. Okay. Now the question is what happens in these cases. Okay. So for L equal to 8, it was proved by Jorgen Andersen that this thing has an element of infinite order. Okay. So level 1, there is this theorem of strange duality of Belkale, where these things are related to theta functions on the Jacobian. That's always a finite monodromy. So this thing is solved. This thing was solved by this thing can be solved by using. So these two things can be solved by using the dualities that we propose here. Yeah. So yeah, this is not yet written down, but one can just modify, because this thing is sort of abelian, and this thing is there is an exceptional isomorphism between SL3 and SL2 and SO3, right? So you can now this thing is abelian, right? Because of this. Which one? Yeah. Sorry. Yeah. So yeah. So what I'm saying is that by
Okay. So L is the level, right?
L is the level, yeah. So what I'm saying is that
Think about this as one of the same as a G1. This SL2 is part of the G1 or a G, because
no, because this is a different one, right?
which one are you using?
Yeah, 3.
Okay.
This one is not semi-simple. It's just the restriction there, right? The restriction is an isomorphism.
But even so, there in that case, L is allowed to be something else.
No, L is 2 in this case.
Okay. But
So
why does it matter? How is it relevant for L equals 4 and 8 and so on?
oh, okay. I'm sorry. Yeah. So what I'm saying is that So L equal to 1, 4, and L equal to 1, 2, and 8 can be tackled differently by using strange duality. Again, not the 8, but the 1 and 2. But I'm saying that 4 was open, and one can tackle 4 in this way, because if I take SO3, then this becomes 4. Okay, and then this is the usual abelian thing, and this thing is known to have finite monodromy, so you can control the monodromy out here from here. Okay, so yeah, I think let me just check if I wanted to say anything else. I think I'm done. Okay, so thank you. Yeah.
If there are any pressing questions, maybe we should ask the speaker. Any questions? If not, let's thanks for the
So many other rank level duality questions remain open. You can go through that list and try to prove all of them. Yeah.